UW campus here is more beautiful than the UW campus I went to. So it's not the same university. I went to Washington. So should first start off by saying this is joint work with my supervisor, Randy. So let's start off with some integer that's not of finite order. So not 0 or 1. We would like to know, and 1 up prime. So P, as always, is a prime. We can always find some A and Z with A mod P generating the group of residues, of non-zero residues. So a natural question to ask would be, can we reverse this? So if we pick our A, can we always find a prime that generates, such that A generates the residues mod P? And does this have a natural density? So, question. For a fixed A in, let's say, Z, not including plus minus 1 or 0, can we always find P prime such that A mod P does the same thing? And the second question was, does the set have natural density? All right, so the first thing I should note is that you can automatically exclude the A, which are squares, for trivial reasons. If A was a square, this will never happen besides P equals 3, or P equals 2. After that, it's not possible. So are there any other conditions on A for which we would expect this to not happen? And the answer is no. So, answer conjecturally, A, yes to both, if and only if A is not a square. Right? And in fact, we can come up with a reasonable density. So what we're asking is, can we find, for this one, can we find a constant dependent on A such that this holds, where pi of x is your standard prime counting function? All right, and the conjecture of Artin was yes, and that C of A is something like, let's see, product of primes Q, let's see, not dividing H, which I'll define in a moment, 1 minus 1 over Q minus 1 times Q dividing H, 1 minus 1 over Q minus 1. All right, where H is the maximum integer for which A is in H power. So right? Okay, this just means some rational constant times this. where these are the important factors. You could argue that I could get rid of this if I were to say rational constant, but it's an important factor that makes sense. So intuitively, this makes sense for the following reason. So I should know. Okay, so intuitively, this is true. So A is a primitive root if and only if for all primes Q, the following conditions do not simultaneously hold. So 1, P is congruent to 1 mod Q, and 2, A to the P minus 1 over Q is congruent to 1 mod P. All right, so if we had a condition where this was true, then essentially what this is saying is that the order can't be P minus 1. It has to be at least, it has to be some divisor of P minus 1 over Q, which means you can't generate all of these. And vice versa, if you had that these were both true, if you had for all primes one of these was false, then you would have to force this. The order would have to be P minus 1, which would tell us that this one's generated by this. Now, and so you notice that this one has frequency 1 over Q minus 1, and this has frequency 1 over Q, right? And so that's where these constants come in. So here, this one will explain, the two of these will explain this, and this one is explained by the fact that if Q divides H, then it doesn't really matter. The second condition is always true. So if Q divides H and A is an H power, so I just write this as B to the H divided by something which divides H, it's always 1. So there's nothing to check there. So that's why you get this second factor. Now, this rational part comes from some dependencies on some fields that we'll see later, but it's not that important. The conjecture should be true, and we do know that it is true on GRH. All right. So. And this is due to Hooley. So I want to look at Hooley's technique mainly for two reasons. I want to generalize the idea, generalize the proof. I want to understand what's really going on with a certain sequence related to this. And to do that, Hooley's proof is helpful, but it's limiting in certain senses. And I want to see both the helpfulness and the limitations. All right, so Hooley's technique. All right, so we noted over here that these two conditions are important, so I'm going to label them. So this will be R, Q, P, and it's true if and only if those both simultaneously hold. So, all right, I need a few technical definitions, but not many. So, I should label this. Let's call this N of X. And so for some Y, I'll just call this quantity the number of primes such that for all Q less than or equal to Y, R, Q, P is false. All right, and you'll note immediately that if I plug in Y equals X minus 1, then I get this quantity. I don't need to go any farther, because once you go past X minus 1, it's not possible for Q to divide P minus 1, which is the order of here. So there's nothing to really check. All right, so this is greater than NAX x minus 1 for all y less than or equal to x minus 1. So that's our desired quantity. All right. So I have some concept. The goal is we're going to relate these two. So I need some kind of bound on the errors. So if the true value tells me when RQP is false, then the false value for this condition will be when this is true. All right, so. And as such, I'm going to define this other counting function. So this is a set of primes such that there exists some prime inside y1, y2 for which R, Q, P is true. All right. So I note I have this quantity, but if I subtract off this quantity, then I've actually counted too many. So I've added in too many error terms if I pick a particular one. So this implies that I have this right before. If I wanted to get rid of the ones where, this doesn't necessarily count all of these, so let's get rid of the ones where it's false. So this just becomes right? Just from, okay, so if I take a prime which contributes here, it will contribute here, and these ones will contribute here. There's nothing to check. It's just basic logic. All right, so the goal is, so this will give us that our desired quantity is our new one plus some error term.
Sorry, do you mean NAXY in the last inequality? Instead of NAX?
Where, here?
Yeah, I mean the last one. Yeah.
No, that should be fine. Where?
Yeah, so you have.
This could be, like, you could say x minus 1 if you want.
Oh, sorry, I mean n.
No. Sorry, yes, here, yes. Thank you. Yeah. Yes, thanks. All right, so the goal now is to count this and then bound these. All right, so in order to do this, I want to relate these two conditions into some algebraic conditions that will allow me to use Chebyarov density here. So note that 1 is equivalent to P splitting completely in Q adjoin zeta of Q. And with 1, two is equivalent to P splitting completely in Q adjoin A to the 1 over Q. The second one might require a little more work, but if you just read Birch's chapter in Castle's Phobic, then it's fine. All right, so combining these two, we get 1 and 2 if and only if P splits completely in Q adjoins zeta Q, A to the 1 over Q. That's nice because splitting completely is a Chebyshev condition. So now I can count the primes for which this splits completely. And so this will allow me to bound these things. So in particular, Chebyshev density theorem and GRH say that this quantity is equal to the logarithmic integral over the degree. And I'll just put it like this. All right, but I want another condition because this is helpful, but it's not that helpful. So all right, so I noted before that these two conditions essentially imply that that the order divides this. Right, so 1 and 2, alternatively, one and 2 are equivalent to Q dividing order, which I'll denote by F. Divides P minus 1 over Q, which is the same as the index dividing Q. Sorry, Q dividing the index. And you can generalize these arguments. So if you want to replace Q with a non-prime, it's fine. So this quantity is one I'll be interested in later. Note that that A is a primitive root if and only if this is 1. So this is really what we're trying to count. So let's tackle this term right here. All right. So N A X Y. So the first thing I do is I'm going to throw in all the primes up to X. That's clearly too many. Now I want to throw out the primes. So what am I trying to count? So I've thrown in all the primes. I now want so that's too many. I want to throw out the primes for which this is 1 and N2 are true. So I just said that this is the same as Q dividing this. So let's get rid of those primes. And I only need to get rid of the primes up to X. So this is Q less than or equal. So Q less than or equal to Y. Right? But this is still too many because now the prime 2 and 3, I've added too many from that because 2 and 3 can still divide the index at the same time. And you continue in this fashion and you're essentially doing the sieve of Eratosthenes. So this is equal to some, like this here. K, Q divides K implies Q less than or equal to Y. Mu of K pi K of X, where pi K of X is just the primes for which k divides the index. Right? Okay. So that's good. I've got this nice formula. I can use this result and just plug in what I'm dealing with, because this was just defined as, well, they were the same. So this is for Q, but the same result still holds for my additional sets when I don't make this prime. So I can use that result to get that this is a constant times lie of x plus big O 5, 6 log x, where here I have chosen y is equal to log x over 6. Right? And in fact, you can choose this to be log x over something bigger than 2. You're fine. The argument still works. All right. So we've got the first part of our argument. We now need to deal with those m's. All right. So. All right. But I've chosen a this, so this is, I can actually bound this using standard, very high school remarks by, let's see, some y1 plus all right, I'm going to deal with each of these separately. In fact, this first one is just bounded by some, let's see, these were primes in between two bounds, so log x over 6 bounded by q, bounded by y1. The number of primes which divides this. Right. This is the same as, I wanted a prime in this range where those two were false, which was the same as this. And so now I can use Chebyshev density theorem and GRH on this again to get that. To get that this is big O x over log x squared. Okay. And in fact, I can push, here I can push y1 up to square root x over some power of log. Let's just say log to the 5. All right, the last term, so y2x. We note that p contributes to this, so contributes to this implies that, let's see, so it implies that the order of A on P is bounded by x minus 1 over y2. Right? So this is, so let me write this in it. This says that there exists q in y2 x. Q divides the index of p, which is equal to yeah, this implies that the order of A divides P minus 1 over Q, and this lower bound on Q gives us that this is bounded by X minus 1 over Y2. So in particular, our quantity of interest is bounded by the number of primes that divide, say, m less than x over y2, a to the m minus 1. Right? Okay. Well, the standard argument could be that this is bounded by, I just take the log, so sum m x over y2 of m, which is bounded by x squared over y2 squared. So, whole thing. So, if we want this to be small, we just choose y2 to equal square root x log x, and that will give us, let's see, x over log x to the 10. So now I just want the middle term. The middle term, just use Bruneti's mark. Right? So you just, this implies that q divides q minus 1, and my lower range is square root divided by some log, and my upper range is square root times some log. So Bruneti's mark will give you the appropriate area term. So. Right, and now, so this is what Bruneti's mark tells us, but you just perform this nice little trick. You multiply by log q and you divide by log x squared. In this range, from there to here, log q behaves like log x, so there's nothing to worry about. And so this gives us x log x over log x squared. So putting these three terms together, and put these four terms together, and we get that that our quantity of interest. So here I should. Get that is equal to some constant dependent on a times the logarithmic integral plus big O x log x over log x squared. All right. Now, this is a nice proof, but I want to generalize it in such a way that I can understand the behavior of these indices. So, the question. Can we understand better the sequence I P as P ranges over primes using who are these ideas? All right. The answer is partially, but in most cases, no. And the problem relies in for example, right in this evaluation right here, it was very important that Q is a prime. If Q is not a prime, this sum is too big, and so I will not get little o of I of x. It was also crucial in some of the other arguments. For example, here, going from this step, going from here to here, let me think. Right, okay, I cannot say this because one useful part here is if y2 is bigger than square root x, then this step here was used the fact that you can only have one prime that does that. If I allow q to be anything, you can have two divisors bigger than square root x. And so I don't really know how to evaluate this kind of quantity if I change q to generic k. There's no way to do it. It's fairly difficult. So we need to come up with a new proof of Hooley's idea that is worse in some regards, but better in the fact that we can generalize this. So, for example, can we determine an asymptotic formula for the set of primes less than or equal to x for which the index is in a given set, S, where S is given. Now, some of Hooley's techniques will work, but not most of them. If you give me a particular set, I can't really tell you what it's supported on. So if it's supported on some random variable, some random set of S, of the natural numbers, you can't really tell me that this argument will work because I don't know if you can only evaluate it on primes. I don't know that information is enough. So we'll need to come up with something new. All right, so let's first prove Hooley's result a different way. So, right, new proof. Right, our desired quantity NA of x is sum of d less than or equal to. Less than or equal to x, the characteristic function of one of the index. All right, so now I'm going to rewrite this function and just switch sums because this is analytic number 30. D divides the index. All right, so it's just switching sums. You rewrite the characteristic function of 1 according to the fundamental property of the Mobius function, and you can get this. So now we break this sum up into the sum of small divisors and the sum of large divisors. So I have these two sums. This first sum you evaluate the same way. You can still use that formula for this quantity using GRH and the Chebyshev density theorem, and you'll still get the stuff you did before that you would have been Hooley. It was just this is harder to evaluate for genericity, and that's why we had to go through a separate method. So this sum is done as before. And it gives us constant dependent on A, logarithmic integral, and some error term which I don't really care about right now. And here, in fact, even Woolley's argument, you can get here y is square root x over log x to some power. We'll use 5 again, it doesn't really matter. Which is important because now we just need to deal with this summation. We need to come up with a new way to evaluate this, which doesn't really care about this function in the front if we want to get some kind of asymptotic results here. All right, so. For the second summation, we'll need a few technical results that I don't want to get into in 2D. So the first one, let's call it A. What I would really like is, so we noticed that D here, this is counting the number of primes that divide the index. So if the index is, so if D is large, that means the index is large. So I need some way of bounding how many primes have large index. So we have the following result. And this is due to popularity. All right, it just says that the sum of the log of the indices is bounded by x log x over log x. So we just miss what you would expect. I can explain that later if you'd like, but this log should not be here. But what this does do is it allows us to say that the index is bigger than y implies that the number of such primes which do that is bounded by, you just divide by log y. So it says so we have some bound on the growth of these indices, or at least the number of large indices. The second result I need is the following. So some tau all right. So what I'm saying here is the sum of the divisors raised to any power is bounded by pi of x. So it's essentially saying, on average at least, that you can't have too many divisors of these indices. So you shouldn't expect them to get too large, or if they do, so this says they shouldn't get too large, and this one says they shouldn't be highly multiplicative, highly composite. All right. And this is similar to So the way you would prove this is using some result of Friedlander and Iwaniak that says that you can always bound generic divisors by some smaller divisor. Some d dividing n, d bounded, so by n to the 1 over, in this case we'll just use 3, but you can change 3 to whatever you want, to any integer you want. Alright. So, I want to bound this summation. I have So what I'm going to do is rewrite this and switch sums again. Right, in fact I can get rid of this view of d. Here we go. Alright, so switching sums. Have I have this. All right. So I have y is bigger than y is less than d, and d divides the index. So I can just shove the condition the index is at least y into the first summation, and I can get rid of this first condition. All right. So this should give me that. Greater than y, and just tau of the index. Right? Okay, so now I can use a, so this first part right here should tell us that we should use a, because that's what this is. The summation conditions are this, and the function here tells us that we should use b. So what you do is you just apply Holder's inequality and pick appropriate conjugates in Holder's inequality. You pick the appropriate conjugates in Holder's inequality. So So this gives us that we have some prime that's not equal to x, index is large to the 1 over s, and this is how the index, the t 1 over t. And so now I just use A and B, and I get, I should know this is GRH. Actually, we can use an epsilon GRH to 1. So A and B give me that this is x log x to the 1 over s log x to the 2 over s plus 1 over t. And now you choose s and t appropriately to obtain this equals our constant as before, and this is x over log x to the 2 minus epsilon for every epsilon greater than 2. Now, we lose out, our error term is worse. That's the first thing I'd like to note, is that Cooley got log x over log x squared, so the epsilon can actually be written as a function of x. We can't do that here, but what we can do is, we note that this argument doesn't really care that I used mu. There's no mu here, there's nothing about square free numbers or friable numbers or anything like that. So I can essentially use this argument on any function that is appropriately bounded by something like this. So I can replace my characteristic function of 1 by a characteristic function of any set. I can also replace it by tau. So I can replace these mu's. So So I can use this technique to show that the number of primes with the index in a given set is equal to some constant dependent on A and S times lie of x plus our error term. Or the sum tau of the index. I can replace these taus by some generalized tau. So this is just the number of ways to write an integer using k non-negative integers. I can also this or this. Here alpha must be less than 1. And so on. Like I can give you a class of functions where this technique will work, and I guess one thing I'd like to note is that these are the first functions that tend to infinity with our index that we know that this is true. So that's nice. We get an actual asymptotic formula. We just miss out on the result of popularity. So A, we just miss it, but I don't quite know how to deal with that yet, because you notice if here I should say that the error term is x over log x 2 minus alpha minus epsilon. So we can't quite get alpha equals 1. If we plug in alpha equals 1 here, this is too big. So we don't really know how to deal with that yet. I'm hopeful that there are some ideas out there that will work, but right now this is the state of what we know about this sequence. And there's an elliptic curve related one, but I won't get into that right
now. Questions?
So you said this new method gets a slightly worse error term.
Yes.
Do you expect that the error term should be something other than what you've got, and it's just that this method can't get you a better one?
Well, the error term seems to be, Hooley's error term doesn't seem to be optimal. There is, if you assume pair correlation conjecture for those fields I wrote down before, you can get a much better power saving. So I'm not even sure what the optimal error term should be in this problem. But getting rid of, let's see, where would the problem would exist? Let's see, it seems here that we would have difficulty, and I don't see any way to get it unless you can increase this, and that doesn't seem likely because Papalari's result, there's a lower bound that's known unconditionally that's too big for this technique to work. So the lower bound is x over log x. You can't improve that at all. It would violate several things in number theory that are probably true. Yeah, so I don't know with that. There might be some other technique that will be able to make this error turn better, but I'm not sure what they are right now.
Okay, let's thank Adam again.